Hey everyone, my name is Taylor Sparks, Editor-in-Chief at Integrating Materials in Manufacturing Innovation. Got a new paper to talk about. It's a new analysis method for the densification of cast ingots with pore defects through upsetting deformation. Okay, so first off, I'm guessing everyone here is already familiar with the difference between cast and wrought metals, right? As cast has a lot of benefits, the net shaping, the biggest one, but wrought has the benefit of getting rid of the pores that are left over in the as cast material. So when you upset it or wrought it, right, when you deform it, you can get rid of some of those pores. And this paper is all about understanding how that process works. If you're less familiar with it, take a look at this first figure. Here they're showing you actually as cast billets, right? And you look at the thing, it looks fine, but then you take a cut down the axial section and you see that there in the middle, there's a bunch of little specks, and those are pores that are left over. Here's a radial cross-section on the right. You see a bunch of those ones in the middle there. So the authors talk about these defects. It's well known that these not only reduce the density of the casting, but then they turn into weak spots. They can be the point whereby local cracks or other problems can basically reduce the service life of your component. And so it would be great to get rid of these pore defects. And one of the most common ways to do that is through high temperature plastic deformation after casting. And there's been a lot of work on understanding how deformation changes and modifies the microstructure, getting rid of these pores, closing them, for example. Some early work by Dudra and Im, Park and Yang goes way back. The point of this paper is to go beyond what's been done in the past, which has been using essentially concepts of what the distribution of pores might look like and replacing that with actual pore distributions, right? It says there's lots of uncertainties about the distribution, quantity, morphological characters. Current homogenized models and idealized configurations just don't cut it, right? They don't capture the actual complexity. So this paper goes beyond that. It's going to actually take heterogeneous modeling for these process-sensitive defects that form. It's going to do a densification analysis of these ingots like real ingots, and then it's going to have a systematic exploration of how the pores evolve under realistic forging conditions matching those with experiment. So we showed you what the actual materials look like. Here's how they make them. They actually talk about how these things are cast. These are 42 chromoly steel billets. The upsetting or the forging that happens afterwards is happening at a high temperature. You're up at 1200 C. It talks about how they're getting it up there. It's under uniaxial compression. They achieve a strain of about 44%. Well, up to 44%. They do different rates. And then they're going to take a look at what the microstructure is doing before and after. So the defect data for the billet they get by taking actually 640 sliced images, right? And the inner slice spacing is 0.5 millimeters. And one of the cool things they develop here is they've got they're taking advantage of the recent advances in the field where you've got the ability to generate 3D pore lattices from these slices. You can take the individual slices and then you can reconstruct an actual defect. And here's an example one. Figure 2 shows you what the voxel point cloud defect would look like. And then on the right, they've actually reconstructed that into a mesh so they can actually pass it through a finite element. So here's a good example of the type of results they're able to generate with this approach. Here they're modeling the effective strain distribution within these billets, on the left in a defective billet and on the right in a non-defective billet. So you can see where the strain is accumulating, where obviously the higher the strain, the more densification we'd expect to see. And that's exactly what we see here. The relative density on the upper and lower axial regions was approximately 0.95 to 0.98 due to the smaller plastic deformation and compressive stress. But the central axial region achieved nearly full densification due to the combined effect of strong plastic deformation and the three-dimensional compressive stress. Here's some examples of what the experimental materials look like after upsetting, right? So you can see this thing that was sort of cylindrical has now been squished and it's bulging out the sides. They can actually look at what the defects look like and analyze them within the material to see what the pore distribution looks like after deformation. One of the things that they modeled in this paper was the effect of friction, right? So you can have different levels of interface friction in the material. And as they increased it, let's see, from 0.12 all the way up to 0.36, the degree of bulging changes. There's an increase in the effective strain and the compressive stress in the central and axial regions. But the effective strain and the compressive stress actually decreased in the axial region. So what's my takeaway from this? Well, by integrating the actual pore microstructure instead of a simulated one, they're able to get a better analysis, a more precise assessment of what the actual forging quality is going to offer, and also some valuable guidance for actual guiding and designing that forging process. So check it out in the latest issue of IMMI.